My name is Jeff Lynn. This is my teammate Meryl Sell. Together we're going to talk to you about infiltration rate and the fluid flow modeling of Orifice drain concrete pavement, which is an alternative to pervious concrete pavement on the market today. So here's a summary of our presentation. First, we're going to go over some stormwater management and pervious concrete. Then I'm going to talk to you about the main tests that we did for infiltration. Then I'm going to hand the mic over to Meryl, who's going to talk to you about mathematical modeling for optimizing this pavement's performance, and conclude with some future research plans that we have. So I'm going to start this presentation off with a very large number. And this large number is 8.4 billion. 8.4 billion was the number of dollars spent on stormwater infrastructure damages due to excessive flooding across the country in 2011. And this is happening because we're paving our cities with and building with materials that are impervious to water, forcing water to accumulate at the surface rather than draining and being absorbed into the soil. And so we have issues such as flooding damages, which is very costly, and it also is a public safety and health concern. So here's a solution that has been tried so far called pervious concrete. And what this is like regular concrete except without fine particles in its mix. And so you just have a conglomerate of gravel glued together with polymers, and this allows water to drain through its macropores, or the gaps between the particles that were once filled with fine materials. And so you get a better shot at this compared to conventional concrete that we use. But although this pervious pavement solution is good for stormwater management, it has issues such as it's expensive, since it's instead of being these particles being cemented with natural materials, it's now cemented together with polymers. And therefore it has lower strength because these fine materials in conventional concrete is really important for strength. And if, let's say you're draining water, but something happens with the pavement and gets clogged and water gets stuck within this pavement. Now water is the only substance on Earth that we know expands when it freezes. And so if water expands within this pavement, then it can force the particles apart and cause it to break and fail. So here's a solution that we developed called Orifice drain concrete pavement, or we'll call for now ODCP for short. ODCP consists of tapered vertical drainage pathways within concrete, and essentially is like conventional concrete pavement in that it has all the fine materials. So therefore preserves much of its strength advantage, and also it'd be easy to cast because you don't need additional chemicals. So what this novel taper does is that if water were to become stagnant in this taper, it can expand freely vertically, reducing the friction within the pavement, the drainage pathway of the pavement, and it's more likely to expand vertically rather than horizontally, breaking the pavement apart and causing it to fail. Another advantage of the taper is that it can be filled with drainage material for pollution, safety, and even flow control. So why is it important that we test drainage or the infiltration rate of pervious pavement? It's because whenever you use, an engineer wants to design a structure for water management purposes, he or she wants to know how much water this piece of infrastructure can manage, and how fast this structure can transport water away from the surface into the soil so that it can be absorbed without minimizing the amount of runoff on the surface. And so here's this standard test that we followed, and it involved sealing a collar to the surface of the pavement while pouring water over and trying to avoid leaks, pouring the water at a constant pressure head level while timing, and taking the time that we recorded for this water to drain completely through, plugging it into an equation, and getting the infiltration rate in what's measured as inches per hour. And so like any experiment, you're going to make a bunch of assumptions and deviate a little bit based on your laboratory and your equipment. You all have experience with this. The major deviation that we had to do was this standard is actually for a field-based experiment, but we did this experiment in the lab. So here's the infiltration rate on the y-axis and the permeable area also, which is the total permeable area of the bottom of the pavement. So that's the sum of total area of the holes which are permeable to water. Let's assume that the rest of the concrete is impermeable to water. And this is because the bottom area of the holes governs the flow. The inflow out dictates the amount of inflow in, assuming that there's no storage. And it's called the continuity equation in fluid mechanics. So here's our first set of results. First we tested the pavement by itself. Then we tested the pavement over a foundation to better get an idea of how this pavement would do realistically. And you can see now that our data is relatively straight, so linear. We're getting a linear relationship, which is good because it shows that this pavement can be very predictable in terms of its performance. And the pavement with the foundation underneath it, to better reflect how it would do on the field, it didn't seem like it varied very significantly from just the pavement by itself, which is good. And we had a range from about 150 to nearly 500 inches per hour, which is excellent considering the average pervious concrete pavement on the market drains at about 300 inches per hour, and a new standard will call for a minimum of about 100 inches per hour, with failure being at less than 10 inches per hour, way down there. Now, the last set of tests that we did involved filling these drainage pathways with filtration material. We just used pea gravel, but as you can see, it's it really restricted the flow rate through our concrete. And this might be an issue because for safety reasons, contractors may right off the bat want to fill these drainage pathways with material. Ideally, we would have wanted to test higher permeable areas, but we were limited based on just two geometries, 1/4 inch bottom openings and 1/8 inch bottom openings, which is extremely small. I would have liked to do 3/8 bottom inch openings for a permeable area of 0.6 inches squared. So just to conclude, infiltration increases linearly with permeable area. The filled orifices result in much lower drainage rates because of the restriction. And orifice drain concrete pavement can be designed to meet a very broad range of drainage requirements, 50 to 100 inches per hour, with 300 inches per hour being average. And with this being said, ODCP has huge potential and is worth further evaluation as a stormwater management practice as an alternative for pervious concrete pavement. And I'm going to pass the rest of this presentation along to Meryl Sell, who will cover fluid flow modeling for optimizing the performance of this pavement on the field.
Great, thank you. So for fluid flow modeling, we decided to start off very simplistically, and as a result, hopefully lead up to more complex models that could output significant information, such as figuring out the ideal orifice pattern within the concrete. So first, we modeled water flow using differential equations shown here. As you can see, the ODCP has one extra differential equation showing the water flowing into the orifices instead of just off the sides as with regular concrete pavement. So from here we decided to do two different modeling techniques. This first model, probabilistic linear motion, we are showing where a raindrop would go, neglecting any initial flows from previous water on the concrete. We are assuming here that once the rain droplet hits the surface, it goes straight in any direction. So it either falls straight into the orifice or falls straight off the sides of the concrete. So this equation here is the probability of a rain droplet at a fixed distance A from the center hole going into that orifice. And to determine the average probability when the distance is at an interval instead of at a fixed point, so for the entire slab instead of just a fixed ring around the orifice, we use the average function value equation, which is fairly commonly used in calculus. Now this gets really messy really quickly, but the main idea here is that we get this graph, which shows basically what we want it to show. As the concrete slab gets larger, the probability of the water droplet going into this small center hole decreases. And if we didn't get this result, we would have known right away that this mess of an equation would have been way off. So the second modeling technique we used was taking into account initial fluid flow instead of neglecting it. So it's definitely a more real-world model and will be pursued with further research. We found that as we were doing tests on the ODCP, the orifice would act sort of like a waterfall, basically a force bringing water to it. As you can see here, the differential equations are the exact same compared to the previous model, but the difference here is that P1 and P2 star represent forces from the initial water flow instead of just pure probability. So for this model, we use distance equations to find the shortest distance to the edge of the concrete. So once this minimum was found, that is the direction that the water droplet would move towards, because that is the direction where the force is the strongest. Also, if the force of moving water into the orifice is different than the force of moving water to the sides, which would be the case in most real-world simulations, this can easily be accounted for using this modeling technique. So there are many future areas of research that we plan on exploring. We know ODCP is worth looking into because of its positive drainage results that Jeff talked about. So for future testing, we would like to compare different orifice geometries that are predicted to be ideal using the mathematical modeling that I talked about, and then see how these tests actually work in the field. We would also like to complete strength and freeze-thaw tests on the ODCP and compare it to its pervious and impervious counterparts. And also, ODCP can be very practical for small projects, but we need to create a relatively automated and efficient production method to be used for larger projects. Because of this, we would like to further develop a large-scale production method that would easily produce pavement like this in the future. As for our future work with mathematical modeling, we would first like to create a more exact model using more complex differential equations, including factors such as the absorption rate of the surrounding substrate, the runoff from surrounding areas, and also the slope of the pavement, such as if it's cast on a hill. From here, it would be our goal to create a semi-automated program that maps the ideal placement of orifices to an entire site plan. So with that, I would like to thank you for your time and open it up to any questions you may have.
With the macroboard type of concrete, out of little bits, is that like regularly like freezing, like crack?
So you're referring to no fines concrete or basically regular pervious concrete on the market. It's the only cast-in-place solution for concrete. And so generally what engineers try to do is we design these pervious concrete pavements so that they drain water away from the surface as fast as possible. Sorry if I wasn't clear about this. And that's why it's important to test infiltration rate. We want a very high infiltration rate. So the higher the points on that plot, the more efficient it is at removing surface water. And in some cases where in the winter the ground might stay frozen and you'll have a surface thaw where snowmelt might sneak into these pores and then freeze again overnight. This could be really bad. It's called a hard freeze cycle. And so not always, but generally for any pavement it's very bad, which is why conventional pavement is completely impermeable. The water freezes, when it freezes, it expands about 10% and pushing about 140,000 psi. So it can really, if this pavement is confined, if it's completely saturated, it's very likely that it can break apart and fail. And a failing would be parts of it chunking off, and just it wouldn't be able to support any weight at all and be very dangerous. Did that answer your question? Thanks a lot.